Good afternoon, everyone. It's a great pleasure to welcome you to the second day of the Israeli Meeting for Autism Research. Today, we will be talking about early childhood, about development and treatment. We have a great lineup of speakers waiting, and we will start with our keynote lecturer. It is really a great privilege, and I'm truly excited to welcome Professor Ami Klin from Georgia. From the US. Professor Klin is the Georgia Research Alliance Eminent Scholar Professor. He is Bernie Marcus Distinguished Chair in Autism and the Chief of the Division of Autism and Developmental Disabilities at Emory University. And most importantly, he's the director of the Marcus Autism Center, which is part of Children's Healthcare of Atlanta. The other really important thing that you should know about Professor Klin is that he obtained his bachelor's degree at the Hebrew University, and he actually speaks Hebrew just as good as any of us. He then went on to obtain his PhD in London, in University College of London, and then moved to Yale. He is a certified clinical psychologist. He did his postdoctoral training at Yale and then became the director of the autism program there. He stayed there until 2010 and then went on to build the Marcus Autism Center. He has done seminal work, really amazing work on early development. And today I'm sure that he will tell us about his eye tracking studies, which have, I think, really revolutionized the field. And without further ado, Ami, it's truly a pleasure to have you here, and בבקשה, הבמה שלך.
תודה רבה, שלום רב לכולם, ואילן, תודה רבה על ההצגה הנדיבה, וגם על ההזדמנות הזו. אני מקווה שבעתיד אנחנו נתראה אישית. So my name is Ami Klin, and I direct the Marcus Autism Center here in Atlanta. Before I actually give you the presentation, I just need to express some thanks and also a disclosure. Most of the work that I'm going to present to you today has been co-created with my colleague Warren Jones. We've been working together since 1998, first at Yale and then here. And this work is funded by the National Institute of Mental Health as well as by other foundations. We always thank the families who have participated in our studies over the years, as well as my colleagues. I also need to disclose that Warren and I are inventors of an investigational diagnostic device that is going to be disseminated by a social enterprise, a company called Early Tech Diagnostics, that is supposed to return any revenues to treatment for children with autism. So as I begin this presentation, I just thought of going over a few points that some of us who have been in this field for a long time sometimes need to rethink. Age of diagnosis of autism is not on set. Yes, children with autism can be reliably and stably diagnosed by the time that they're 2 or 3 years of age, but really the onset is in the first year of life. It's not a rare condition. It's the most common complex neurodevelopmental disorder affecting about 2% of the population. And we grew up thinking that autism and intellectual disability were almost synonymous, but that's not true. The prevalence rate of intellectual disability in autism is about 33%. And what we have learned over the years is that the greatest burdens of autism, the intellectual disability, the language disability, and severe behavioral challenges for the vast majority of people with autism, these are not part of the definition. These are the results of having autism. And finally, since I'm going to talk about diagnostic things and screening, it's important to know that in this field, false positives mean something quite different, because there are many children who are screened positive in early detection efforts. A lot of those children actually have other actionable developmental delays that would benefit from early intervention as well. So just keeping those things in mind. Well, autism is an enormous public health challenge in the US and elsewhere. 1 in 54 children. I go home every night thinking that 73,000 children will be born in the US every year who will have autism. The societal costs in the US are huge, over $120 billion a year. And the lifetime cost of care per child ranges from 1.5 to $2.4 million. Imagine then the economic burden on families. The good news is that with early detection and intervention, one can truly optimize outcomes of children. And this is not a controversial statement. The American Academy of Pediatrics has been recommending that since 2007. And yet, the median age of diagnosis has been stuck at around the ages of 4 and 5.7 years, which basically means that more than half of all children diagnosed with autism are diagnosed during their school years, when we are no longer necessarily treating their autism, but we're treating all of those other burdens that we discussed. One of the major issues is access to diagnosis, which in turn gives you access to intervention. There are just not many expert clinicians. In fact, when we think about the gold standard diagnosis of autism, the 5 to 6 hours evaluation by expert clinicians, this happens in the US in less than 6% of the entire population of kids. So this is a huge issue. But with the public health challenge comes the opportunity. And those opportunities, they come from the new science. Autism is the most strongly genetic of all complex neurodevelopmental conditions, but the genetics is very complex. There are hundreds and hundreds of genetic variants that have already been implicated in autism, and only a very small minority of children actually have highly penetrant monogenic conditions. The vast majority of them, they have a lot of variants that are basically contributing very low effect sizes. And one tends to think about the genetic liability as directly related to the symptoms of the condition. But what we've learned is that this is not so. That genetic liability, those genetic risks, they disrupt normative development, normal development. The results thereof become autism. And if so, were we to be able to normalize early experiences early on in life, we might be able to alleviate the emergence of symptoms as well as to optimize children's outcomes. One of the constructs that we have been advancing is this of a growth chart. The CDC, which is about half a mile from our center, has advanced those growth charts of physical height and weight and head circumference. What we've been trying to do in our work is to create the same kind of growth charts, but in the social domain, in social development. Disruptions thereof put a child at risk for autism. So let's think about the beginning of life. Babies are born in this utter state of fragility. Without a caregiver, they would simply die. So imagine, this is a cartoon from Mad Magazine. Imagine that the baby is born in a complex environment with a whole bunch of things around that baby. But what is that the baby sees? The baby sees people. And the babies see people because people are absolutely essential for their survival. In fact, anything that sounds like caregivers, anything that smells like caregivers, anything that moves like caregivers, anything that looks like caregivers, anything that interacts like caregivers is going to command preferential attention of that baby. And so these are the three constructs that really form the platform for the developmental social brain. The first one is that babies are born readily to orient to others because their survival depends on them. But what really moves development forward is reciprocal social interaction. Basically, the mutually reinforcing choreography that happens between the baby and the caregiver, and then through these cycles of contingency, move development forward. So keep that in mind, because that also determines the kinds of interventions that we're going to put in place early on in life. And the third construct is that of neuroplasticity. We need to remember that in the first year of life, this is the period of lifetime maximal plasticity. By the time that we celebrate the baby's first birthday, brains have doubled, and synaptic density as an index of the organization of the brain, the complexity of the brain, quadruples by the time that babies are 1 year of age. Therefore, if we would like to alter the developmental trajectories of brain development, we have to take this window of opportunity afforded by neuroplasticity. So remember, reciprocal social interaction, placing a child in front of a television speaking Chinese is not going to have that child speaking Chinese. It's not sounds or lights. It's really the active engagement of another human being. Now, given all that I've told you so far, let's take a look at this little girl that we saw many years ago. At the time, she was the youngest child ever diagnosed with autism at the age of 15 months. So take a look.
You're blocking the stuff you remember. You had to, oh yeah, you had to put those things. So let me do one thing here.
So this little girl really influenced the creation of our labs and the kind of research that we wanted to do, because I grew up as a clinician seeing a lot of babies. And this child appeared totally isolated and ignoring my approaches, even if I was just a few inches from her nose. So the question is, what happened? She couldn't see me, she couldn't hear me, but then 5 minutes later, she does this.
Haley up. Haley up.
So what happened is that, well, you see the state of disrepair of the playrooms at Yale, but she ignored me 2 inches from her nose, but she saw an M&M, a little piece of candy about 5 feet away from her. So that was the hypothesis. The hypothesis is that unlike in typical development, when children are born to orient, children with autism are born with this attenuated sense of the other. And that basically sets them on a path that is quite different in terms of their experiences. If you're following the upper trajectory, you become an expert on people. But if the world of things is what commands your attention, you become an expert on those experiences, on things, ever more complex things, but things nevertheless. So we set up an entire research program to understand the mind of this little girl. And one thing that we did was, how could we possibly measure those experiences? So we leveraged this technology of eye tracking to try and see the extent to which we could see the world through the eyes of individuals with autism. And here you can see our old lab for infants. This is Warren Jones, my colleague, and a 5-month-old little boy. And so there he goes, and he's happy. He's watching a mom-like figure trying to entreat him. And as he's doing that, we are measuring what he's looking at 120 times a second.
Right, left, right.
So when we started doing this research with babies, and we have one of the NIH Autism Centers of Excellence. It's now in its 4th generation, 2 at Yale and 2 here at Emory. And we've been following babies from birth. These are the younger siblings of children with autism, as well as typical or low-risk babies. The younger siblings of children with autism, 1 in 5 of them will also develop autism, and another 1 in 5 will develop something similar. So that's our way of studying infant development. And we see those babies monthly all the way to the age of 30 to 36 months. So here is that typically developing boy, that 5-month-old boy, as he is looking at a caregiver, and I'm showing this in slow motion to you. You see a cross in the middle of the screen. That cross there tells you exactly where he's looking at. So let's take a look. So what you see is that little boy is falling in love with that mom-like eyes. And the eyes are not only the window to the soul, they're also the window to social neuroscience. It's one of the most foundational mechanisms of socialization. In fact, we do analogous studies with infant monkeys, and we see the same thing. And now you see a growth chart of eye fixation. So fixation to the eyes of the caregiver from the age of 2 months to the age of 24 months, okay? The top is the actual curve of percent fixation time, and the bottom is the first derivative, or change in fixation. So you see that eye fixation goes up for the first 6 months or so, and then it decreases and increases again towards 24 months. The reason why eye fixation decreases at around 6 to 9 months is because mouth fixation increases. And it increases because babies discover that something important is coming from their mom's mouths, and that is speech. In fact, increased fixation to the mouth is a biomarker for the acquisition of the first words that children express. So here you see, this is for typically developing babies from the age of 2 to the age of 24 months. Now, let's take a look at a 5-month-old who was later diagnosed with autism. Let's see what he does. So what we found out is that those babies who are later diagnosed with autism spend a lot of time looking at that mouth. And in another sort of research line, we studied this phenomenon. Children with autism tend to focus on the mouths because of audiovisual synchrony, the fact that lip movements co-occur, or they co-vary with speech sounds. So this is a physical contingency that commands their attention rather than the eyes, and the eyes are, of course, a social contingency. So what happens in terms of those growth charts? So remember, this is for typically developing children. What do children with autism do? Babies that we follow from birth all the way to 24 months. And here you can see, it starts all the way up there and then is free fall for the first 24 months of life. It's the curve in red. And then we had another cohort, and the results were very similar. So we feel very comfortable with this finding. So we see that those disruptions are really happening from as early as we're able to measure it. And the feeling was that this was quite foundational. And because autism is such a strongly genetic condition, we wanted to know the extent to which this eye tracking assays of something that we call social visual engagement is a mechanism of socialization, the extent to which those things were genetically determined. And so we conducted with our good friend John Constantino at Washington University a very large study of twins, monozygotic twins, identical twins, and fraternal twins, and trying to see what we would find. So in this sample of twins, one twin would watch those videos in one room, and the other twin of the twin set would watch those videos in another lab, okay? So here is an example. I'm bringing the data together so that you can observe both twins at the same time. But remember, they're watching this thing separately. But you should be seeing two crosses on your screen. This is now for fraternal twins. And now I'm going to show you identical twins. Remember, they're watching those things in separate labs. So when we quantified that, that's what we found. So let's start from A. These are non-related, non-sibling random pairs. And what you see is that there is very little agreement. And then we match on age and sex, and there is a little bit more of agreement. But for fraternal twins, there was agreement of 0.35. But for the identical twins, the agreement was of 0.91. And as you know from the classic twin design, it is the difference between the 0.91 to the 0.35 that gives you a sense of the genetic determination. And so we could come to the conclusion that looking at people's eyes and mouths, well, those things are under very, very strict genetic control. Now, what about more complex situations? So these are now fraternal twins watching a very complex social situation. Now, compare that now with identical twins. Remember, they're watching this in separate rooms. Well, when we quantified those measures, and I'm not going to sort of go over each one of those graphs, but this is what we found. what we found is that identical twins relative to fraternal twins were more likely to move their eyes at the same moment in time. In fact, at microscales of milliseconds, we're talking about 100 milliseconds, about 2 synapses away from the eye, as it were. But the identical twins are also more likely to move their eyes in the same directions. And they were more likely to move their eyes onto the same semantic content, for example, faces. And what we found remarkable is that these very same markers of social visual engagement that are really under strict genetic control, most highly heritable, were also those that would segregate children with autism. Here you see density distributions for the typically developing twins relative to percent fixation to mouth and eyes. Now, the little balls in red are toddlers with autism. So these are all 2-year-olds. These are toddlers with autism. They are segregated at that level. And then this is the first group, and then there was another independent cohort. So the very assays that are under strict genetic control in social visual engagement are the ones that also segregate autism, which gave us the sense that this might be an endophenotype. That is something that actually that happens in families. So to summarize, eye and mouth looking is highly heritable. There is also high probability, genetic probability, or genetically based probability of those children moving their eyes in the same moments, at the same direction, same content, at microscales of milliseconds. And so here is the notion that they were not only reacting to the videos, they're also seeking information out there in the social world. In fact, they were creating their own niche. They were actually building their own world. And needless to say, yes, there is a timetable for brain maturation, but brain is exquisitely influenced by the experiences that a child has. We know that those experiences, they not only shape brain, they also mediate genetic expression. So we are very interested in this phenomenon. Joe Ledoux, a great neuroscientist at NYU, this is the subtitle of one of his books, How Our Brains Become Who We Are, or How Our Experiences Become Our Brains. So in many different ways, brain structure and function are physical instantiations of those lived experiences. In fact, I'm just going to do a little bit of an illustration here for you. We have been, at the same time that we are studying children through these behavioral assays, eye tracking based, we also study brain morphology, connectivity, and tractography through DTI. And we actually complete 3 brain scans before the babies are 3 months of age. And here is an illustration of this work done primarily by my colleagues Sarah Schultz and Lan-Chuan Li. What you see on the left-hand side at the top are growth charts of social visual engagement, percent fixations to the eye, mouth, body, the background. And on the right, you see FA values of white matter maturation that we measure along many, many different circuits. And at the bottom, what you see is that eye fixation at around the age of 60 days of life is highly predictive of white matter microstructure maturation about 60 to 90 days later. This is just one example focusing on the inferior frontooccipital fasciculus. But the notion is that we actually have here an instantiation of that hypothesis, that indeed early behaviors or early experiences have an impact on brain development. But what kind of world is this little girl creating? Because we know that her experiences are also shaping her brain. In order to address this question, we really needed to find a way of measure how children look and experience those kinds of situations. Well, these are the kinds of experiences that shapes a child's understanding of facial expressions and of intentions and of communication and of all of those sort of things. So it's really critical for us to understand how children are processing this kind of information, since it's so critical for brain development. So in order to show you the methods that we develop, here is one frame of video. Remember, there are about 30 frames per second in that video. And this now is an equation. This is one two-year-old focusing on that spot of the screen at that moment in time. And that's the amount of visual resources that that two-year-old is dedicating to that spot on the screen at that moment in time. What do I mean? I mean that we use the mapping of photoreceptive cells in the monkey brain, in the monkey eye. And as you know, the amount of resources that the child dedicates to a point on the screen has to do with the concentration of those photoreceptive cells, which translates into cortical magnification, truly into brain surface. So this is the amount of visual resources one child dedicating to that spot. Now, you're going to see 45 two-year-olds watching that frame of video. And when they converge their gaze on one spot, you see that the colors are getting hotter. And the reason why they get hotter is because there is a collective investment of resources, of visual resources on that spot of the screen. Let me give you a different perspective now, the bird's eye view. We call this bird's eye view a salience map. And we call it a salience map because now you have a frame of video and you see that one portion of the screen is hot colors like orange and red. That means that most of the kids are focusing on that spot of the screen. Now, if we do that, we'll be able to watch that entire video through the eyes of those 45 two-year-olds. So let me stop here for a moment. You see, I'm just going to go frame by frame. Nothing happening, nothing happening. Oops, something happened there. And then, whoopsie, something really, really important happened there. So we can actually measure those collective patterns of looking as we see that video. Now, let's take a different perspective. So remember, that's a salience map. Now, this is one frame of video, but of course, there are many, many, many frames of video, in fact, 30 per second. Now let's carve out that salience map across time. And what we end up having is a space-time distribution. And we call that space-time distribution a funnel of attention. And when you see that funnel getting really red, it's because it is statistically significant. What does that mean? It means that those children are focusing on the same spot at the same time, okay? Now, if you use this method, we can now, again, watch that video and look on the left panel. And the left panel tells you exactly where the children are focusing on, okay? Now, I'll stop here for a moment. We call this hotspots of socialization because why they are hotspots? Because since all of the typically developing children are looking at those things, obviously, those aspects of the video are entraining the children. There are enculturation experiences that are basically out there in the environment. What is most important out there in the social environment? Okay, let's take another look. And I'll stop right here. On the left panel, you would see that red that all of these typically developing two-year-olds are looking at. Look, they're not looking at either of the children, but the reason they're looking where they are looking is because one of the toddlers is giving a gaze cue. This is called a joint attention cue. The child is looking at the object in between the two children. That's the, let's say, that's where the action is in that social interaction. And you see that all of these two-year-olds were sensitive to that cue. And those kinds of statistical convergences, those funnels of attention, they happen hundreds of times in a 5 to 6 minute video. In fact, we are astounded that those typically developing two-year-olds, they watch those videos 80% of the time. They're looking at the same spot of the screen at the same time. Now, here is one example. So here is a typically developing attentional funnel for that frame, okay? Now, these are now what you're seeing in green are scan paths of 2-year-olds with autism crossing the same frame. This is where the typically developing children are focusing on, and this is where the children with autism are focusing on. So they are watching the same video, but their experiences are entirely different. And remember, what shapes brain is the experiences that the children are having. As I mentioned to you, those things happen hundreds of times. And what we found out is that in a 5-minute video, like those videos, like that video that I just showed you, there are over 570 divergencies between the toddlers with autism relative to the typically developing toddlers. So you could see this as missed experiences of social learning. And if you extrapolate to real life, they would lose thousands and thousands and thousands of social learning experiences in 2 hours and millions in a whole year or 2 years of life. So this is the construction of autism that you see. So autism, in a way, it builds itself moment by moment through those divergences, through those missed experiences of social learning. Needless to say, those experiences are going to shape a very different brain. If you want to see here one situation, the top are typically developing toddlers, and the bottom are toddlers with autism. So you see how different their experiences are? Oh, I forgot to tell you, there is a happy ending to that video. Now, you can see at the top where the typical toddlers are focusing. They're focusing on the climax of that social situation. The fact that the two children have reconciled, but the children with autism in the bottom, they are all over the place. They watched the same thing, but they missed the meaning of that video. So we then decided to try and see if we could leverage this kind of science to create, to increase access to early diagnostic services, because that's one of the major bottlenecks for increasing access to early intervention, which can really, really change the life of a child. So we used this methodology that I showed you before. We used that to create normative data sets. So now we know what typically developing children do when they watch a bunch of those videos. And each one of those statistical convergences becomes an experimental press against which we can test what a child with autism does. And those are hundreds and hundreds. You see there are some of the scan paths, I believe in red. These are children with autism relative to that typically developing attentional funnel. So then we did a study. And in this study, we first had a discovery cohort. So this study was about 1,059 children. The first was a discovery cohort in which we used in order to generate this model that I just showed you. And then there was a replication cohort. This replication cohort, about 370 children, all seen away from our labs. This was entirely done using a standalone device in a community health center about 50 miles from Atlanta. And what we tried to do is that this discovery cohort, which is entirely lab-based over the years, this was used in order to generate a model. The replication cohort was with a standalone investigational device in this community health center. We used about 14 videos as stimuli, about 53 seconds each, about 12 minutes, 13 minutes of videos in total that these children watch. And the study was to try and see the extent to which we could accurately assess the presence of autism relative to not autism, but we also wanted to model the severity of the condition in these children, the severity of the autism, as well as level of ability of the child. We followed those kinds of really reference standard guidelines for the testing of any diagnostic study: prospective, broad spectrum of the population, consecutive referrals, complete diagnostic verification using gold standards, and entirely double-blinded. So the clinical team did not know what the eye tracking team did, and vice versa. And here are the results. Focus on the middle of this slide, because those are the results that matter, because this is for the replication cohort. When you run ROCs, it's important for you when you read papers in the literature. When you look ROCs for accuracy of any diagnostic study, obviously you're going to achieve a high level of accuracy in your discovery cohort because you use the discovery cohort to generate your model. So the results that really matter are the replication cohort for those, in this case, 361 children. So we're very happy with that because we have sensitivity of over 83%, specificity of over 82%. We're feeling that this was a 12-minute procedure relative to a 4 to 6 hour clinical evaluation. So we thought that this would provide the cost-efficient solution. Now, what about the false positives? This was something that we were interested in. When we start to sort of diving into the clinical files of the children who receive false positives, we start seeing all of those kinds of clinical notes. A lot of concerns about the development of the children. And when we summarize this, 80% of false positives via our eye tracking assays were given a different clinical diagnosis. So language delay, for example, global developmental delay for 25% of the children. And then there were all of these kinds of insecurities or lack of confidence on the part of the clinician, seeing those primarily 2-year-olds with a lot of subthreshold diagnosis, but not a formal diagnosis. And when we look into that, half of the children given a provisional subthreshold diagnosis were later given an autism diagnosis about a year later, because we followed those children for a year after this experiment. But we're also interested in trying to model the level of severity of autism. And what we modeled was the ADOS, the Autism Diagnostic Observation Schedule, which is like a reference standard for really trying to quantify the level of the disability, right? And these are the results. The result is that with this 12-minute experiment, we could capture about 78% of the variance of the ADOS, which again, a procedure in itself that can last for about an hour with a toddler. And remember, this is a 12-minute experiment. We also were able to model verbal ability. We modeled the Mullen early scales of learning, the verbal scales, and we could capture about 63% of the variance. And we could capture about 50% of the variance of the Mullen nonverbal scale. And it makes sense because what we have is a social information processing procedure. We are basically measuring social ability and disability. And verbal ability is much closer connected to socialization than it is nonverbal. We have a lot of children with autism who have terrific nonverbal skills. So once we got those kinds of results, we started looking into the possibility of going for FDA clearance for this particular device. And then we run a pivotal FDA-registered national clinical trial in 6 sites in the U.S., about 505 children, actually, not 503. Seattle Children's Hospital, Cincinnati Children's Hospital, Rush in Chicago, University of San Francisco, University of California, San Francisco, Sark in Phoenix, and here at Emory. And this is what it looks like, the procedure as we run this clinical trial.
Yeah. Just like the car. It's just like the cars. Let's bring them in here.
So the idea is for us to have a procedure that will require only an operator and not expert clinicians. This is what the child sees. It's entirely automated, so the operator can complete the procedure. There's a whole bunch of quality control sort of devices built in.
Good job. Yeah, you're ready to get out, huh?
So we're happy with that because we plan to analyze all the clinical data by by September 1st, and then hopefully we'll be able to submit what's called here in the US a 510K submission for FDA clearance by April of 2022. We are happy with this because this is not to replace expert clinicians, but this is to provide access to families that don't have access to expert clinicians. In that way, overcoming a major barrier to early intervention. So we need to create solutions that are high throughput, low cost. We need to promote early detection and early intervention in this fashion. In this way, attenuate the emergence of symptoms and alleviate the emergence of intellectual disability and all of the other burdens. And the idea is to support a system that is that basically does not have expert clinicians at a number that would provide access to families nationwide, and I am sure in other countries as well. And we're using assays that are under genetic influence. And so people would probably say, if this is genetically based, what's the point of early intervention? Well, you saw what I discussed today. What children do is that they co-create the world with the environment, the social environment in particular. What they're going to focus on and their search of information and environment is under genetic control, but we might be able to engineer that environment. And in that way, we will be able to alter this children's experiences and therefore promote their development. So that would be unethical to have a solution for early diagnosis if we didn't do, if we didn't put enough energy and resources into increasing access to early treatment. So we have a whole bunch of collaborations in the US establishing modes or modalities of early treatment that are supposed to be community viable. And in the US, evidence-based early treatment is caregiver mediated. So we work with parents, and you're going to see why. But let me show you, this is one of our colleagues, Amy Weatherby. There are other colleagues who are part of this network, Kathy Lord at UCLA and several others.
Babies learn to talk at an amazing rate. They go from sounds to words to sentences in the first 2 years. Before they can talk, babies watch what you do, listen to what you say, and try to figure out what you mean. Every month, babies reach important new milestones, but the ones that matter most are the ones that come before they can talk. Our social communication growth charts can help you learn these critical milestones. Explore hundreds of video clips that show you how to support your child's learning in ordinary, everyday moments. Chart your child's development to monitor which milestones they've reached, which are emerging, and which ones to look for in the coming weeks and months. Everything you do and say matters, especially during this critical time when your baby's brain is developing the most rapidly and is shaped by the experiences you provide. Learn how to turn everyday activities into learning moments. Every moment counts and learning never stops. Find out what's in store for your baby each month. This is the most important role of your life.
So this is one of the videos that parents see. The idea here is to really build on, remember how our children, the children with autism, they were missing social learning experiences at the rate of hundreds within a 6-minute video, thousands over the course of a day. So the idea is to really engineer the daily experiences that mothers and their babies or caregivers and their babies have, and basically build the kinds of temptations, the kinds of things that we do in speech, language, and communication therapies as part of the routine that the child has at home. Now, this is not a therapist working with the child. This is actually the mother working with the child. And that mother has a bug in her ear, like an earphone. And she's being guided by interventionists who are in the building and who are providing this form of remote coaching of parents who are far away. By creating this online suite of tools, we're able to train parents, pediatricians, and early intervention providers on those techniques. I have there those two sites that might be resources to you for babies. It's called the babynavigator.com, and when the child already has autism, the autismnavigator.com. But those sites have courses and hundreds of videos that show what a typical behavior is and what is a symptom of autism. And in the Baby Navigator, we have all of those growth charts that allow parents to basically monitor their own child's development and learn ways that they can promote and advance that development. And the idea here is to really build those kinds of therapeutic moments in everyday experiences of the child, doing routines, whether it is cooking or playing or brushing one's teeth. The notion is that we start by creating this common agenda between the caregiver and the child, moving on to achieving social reciprocity, and then advancing things such as language and play skills. And the goals for those interventions, this is called the early social interaction modality, is for the parents, first of all, as they are the transactional supports. They are the enablers. They are the affordances for the child to acquire those skills. So the goals are both for parents and for child. And the notion is that we build those things on interactions or on experiences that babies and caregivers have every day. And the notion is that parents are seeking guidance. They are anxious. They are looking for some form of empowerment, and those interventions can be very helpful. And what we have found out is that those kinds of, because there's only one platform for brain development, that those kinds of interventions, they are not only beneficial to kids with autism, but they're beneficial to a whole bunch of children with genetic conditions, with medical conditions, and also for children who grow up in disadvantaged backgrounds. And the notion here is that we believe that the developmental medicine of the 21st century is going to focus less and less on curing diseases, because those conditions that we're talking about from a causation, from an etiology standpoint, they are enormously complex. We don't need to wait until we have the cause of every one of those conditions. There are going to be multiple to start optimizing their outcomes. And we can do so by universal screening, by increasing access to identification and to early intervention in ways that are community viable. Now, those kinds of things that we're bringing into the field of autism, those interventions have been used in other domains. My good friend Jack Shonkoff at Harvard has been doing what he calls the steps for brain building, the serve and return, for years with children who are maltreated. My good friend David Willis is the head of HRSA, focusing on low-income families and the need to provide them with the supports that the parents need in order to promote their development. Here in Georgia, we focus on language nutrition, creating language-rich environments for children. And this is a public health campaign called Talk of Me Baby. The notion that very vulnerable pregnant teens, for example, they don't feel that they can play a role in their child's development because their lives is in chaos. But in fact, they have a very important role to play by creating these language-rich environments. Okay, let me summarize everything I told you today. Autism is a massive public health challenge, an enormous public health opportunity. Children's lifetime outcomes can be optimized with early detection, increased access to diagnostic services and to early intervention services. Remember that the greatest burdens of autism that are terrible for child, for family, but also as a societal cost to the health system and education system, the intellectual disability, the language disability, the severe behavior challenges, those things are not inevitable and can be significantly ameliorated. I showed you some of the assays that we have been used to quantify that, and I've told you that those are under strict genetic control, but we can actually engineer those environments by training parents, building on everything that they do every day with their babies to create situations of greater engagement. Remember the hundreds and hundreds of missed experiences of social learning if we were able to address this, the children who have a completely different developmental trajectory. But our solutions need to be accessible because our field is plagued with healthcare disparities. In the US, for example, the burden of intellectual disability among African American children with autism is almost double relative to white children with autism, all having to do with the lack of access to diagnostics and to services early on in life. And our feel is that those kinds of methods that I showed you today, they are not only beneficial to children with autism, 2% of the population, but they really can be very beneficial to a much larger group of vulnerable children, 10 to 12% of the population, whose early brain development is disrupted by vulnerabilities of genetic, medical, or environmental natures. Our goal is this, is to really reduce autism to a different way of being in this world as a trait, and to truly change the narrative of autism from one of disability to one of diversity. Thank you very much. So I think we have some questions.
Thank you so much, Ami. That was really inspiring and an amazing talk. We do have a few questions. I think I can actually group some of them. One, there are two questions about the issue of age, and whether you have anything to say regarding the reliability of findings across ages, what happens when you look at older ages, maybe even going into older childhood and adolescence.
Yeah, so, and I imagine that this is in relationship to the device and to that work that I presented today. Yeah. We made a very conscious decision to focus on children age 16 to 30 months. The main reason why we prioritize that is because in the US, we have a federal mandate. Every child under the age of 3 years should receive early intervention services. And yet, only there are 700,000 children with autism who receive special education services during their school years, but only 1 in 5 is identified before the age of 3. So even though we have a federal mandate, the children don't access those services. So the reason why we prioritize that age, and that's going to be the FDA indication, is really 16 to 30 months. Now, we picked a very bad time because even for expert clinicians, people like myself, it's much more difficult to make a diagnosis of a younger child than an older child. There is less stability early on in life than later on in life. So we have been conducting those kinds of studies of older individuals than 16 to 30 months. And there, the situation is much more clear. And there, the accuracy is much higher because autism is much more delineated later on in life. But we also downward extended that. So now we have a very large NIH grant that extends this technology to 9-month-olds. And so one of the projects that we have, we put those devices in vans. We're parking those vans outside of pediatric practices. In the US, just like Tipot Chalav that you have in Israel, children need to come to a 9-month well baby checkup. And so at the same time that the child is coming to the well baby checkup, they're going to step into our van and they'll complete this procedure. And the idea is that we want to test the power of this technology for screening community-wide, no longer by referral, community-wide, and the power of diagnosis at that age group. So that's what we have. Now, in that 2013 paper that I showed you, those growth charts that I showed you before, we were able to identify, let's say, deviations from normative really from the age of 2 months. But the quantification that we achieved for this device is of a different level of magnitude relative to that early work in 2013. Mm-hmm. Better.
Great. So there's another question about trying to maybe press you on the distinction between screening and diagnosis, and whether, you know, so I'm just putting myself in the shoes of physicians. They might feel have a hard time with a machine diagnosing autism.
Yeah, and I understand that. So when I talked to my good friend Kathy Lord, who authored the ADOS and ADI, she's going to say, God, no, right? Never, ever, ever, ever will I allow for a child to receive a diagnosis of autism from a machine relative to me, an expert clinician. So to that, I state, as per CDC, fewer than 6% of children with autism who receive a diagnosis in the community completed an ADAS. Fewer than 6% in the United States of America, right? So the issue here is not to replace Kathy Lord or replace Amy Klin. The issue here is, I just mentioned that the field of healthcare disparities is huge in autism. What I stated is unconscionable. Black children with autism have double the rates of intellectual disability than white children. This is not due to genetics. We just published a paper, John Constantino, Dan Gashwin, and myself, in pediatrics about the timing of diagnosis of Black children in the US. If you study that diagnostic odyssey, that argument becomes moot, because the issue is, if everybody could see Kathy Lord, that would be wonderful. But no, and particularly if you are minority, if you are low income, or if you are in rural areas of the United States, you won't see an expert clinician. That's what this diagnostic device is for. As for the notion of screening versus to diagnosis, you know what that research shows? First of all, the most widespread screening instrument in the US is something called the MChat. The MChat has sensitivity, basically false negatives of 61%. False negatives. So we are missing more children than we are identifying. Okay? Now this is one. Look at Whitney Guthrie's new paper that she did at CHUP. Now, 50% of the kids who are screen positive never make to diagnosis. They never follow up on their screen positive. And another 50% with a diagnosis never make to early intervention. So we need, from an implementation science standpoint, from a public health standpoint, we need to bring, screening and diagnosis closer together. Because if we are at the downstream from the MChat that has a rate of false negatives of 61%, we are going to continue to have the same thing. So we have a procedure. That's the reason why we are studying this as a screening, a community-wide screening as well. It's a 12-minute procedure. So yes, it is brief, it is cost-efficient enough, it is objective, and it's quantitative enough to serve as both a screener and a diagnosis. So that's my answer right now.
Yeah, and really emphasizing reducing those horrible delays. I had one other question that I wanted to ask. In your presentation, on one hand, you have this experience dependency, where the experiences that the child has during early life are shaping their brain and so on, and creating the autism. And on the other hand, there's this strong genetic component that is actually influencing this, which means that there's a biological or multiple biological factors that are playing there. And does that mean that there may still be opportunities for intervention that do involve those aspects, in addition to all of the behavioral aspects that you've talked about?
By all means, Ilan. In fact, this is a big, our Autism Center of Excellence, which is a P50, it's a large project, only 5 in the country. It's entirely focused on addressing your question. In our eye tracking studies, and remember, the same studies that we do with human babies, we do with infant monkeys. So we have that as a model system as well. But you may have noticed when I was showing those growth charts of eye fixation, that the children with autism, they started at a higher level still than the typical children. And then it was free fall. So what we found out is that, in the first 4 to 8 weeks of life, babies have reflexive behaviors. They are experience expectant, and they are subcortically guided. Between 4 to 8 weeks and about 12 to 16 weeks, there is a transition that happens to experience dependent, voluntary, interactional, and cortically guided behaviors. And so our hypothesis is that, in fact, I was wrong. When I wrote my dissertation back in 1988, I said that children were born with an attenuated sense of the others. We were wrong. What we're showing now is that the children are not born that way, that those reflexive skills are there, but they don't make the transition that happens between 8 and 12 weeks of life. And fascinating to us is that the same behaviors that we are seeing, the same evidence in babies, we are seeing in infant monkeys, except that everything happens with them 4 times as fast because you need that transformation. But it's more than that. We are seeing brain as well, both in connectivity and in tractography, in human infants' brains and in infant monkeys. So we need to better understand that transition to answer your question, because we are also began an entire field of research focusing on epigenetic assays, both gene expression and DNA methylation, because I told you that experiences are also mediating gene expressions. So what we are trying to do, and we are creating literally hundreds and hundreds of those growth charts of longitudinally obtained gene expression and DNA methylation assays, because these are peripherally, right? Peripherally obtained. These are blood. And we did that with rodents, and what we want is to find signal to brain. As you know, every cell in our body expresses genes differently, but we are particularly interested in bringing all of this together. You saw some of the circuitries that we are particularly interested in. So we're trying to get signal from epigenetics onto brain, onto behavior, because, and that's the last thing I'm going to say, you probably know about brain span. So the brain span work that my good friend Nat Seston has been doing at Yale tells us that there are some genes, and we published this in 2018 in Ticks, there are some genes that have maximal expression for the lifetime during that period of time. So those are the genes that we're going to be looking into first, because the idea is, were we to be able to identify them, we could upregulate them or downregulate and maybe change that genetic predisposition. Does that make sense?
Yeah, that ties everything together, and I think we won't have a shortage of work in the coming years. There's quite a bit to do.
Okay.
So, Ami, thank you so much for this wonderful hour that you've spent with us, and really a true honor to have you here, and we'll see you in Israel soon.
אז תודה רבה לך, תודה רבה לכולם ששמעו אותי עכשיו, וחבל שזה במצב כזה, אבל אני באמת מקווה שבעתיד אנחנו נתראה אישית ונשתמע, ואנחנו נהיה בקשר גם, שאנחנו נוכל קצת לבוא ביחד. אתה היית צריך להיות פה, ואחר כך אני הייתי צריך להיות שם. אני מקווה שבעתיד הקרוב אנחנו נתראה. אז כל טוב לכם.
תודה רבה, עמי. ואנחנו נעבור הלאה להמשך ההרצאות.